Okay, physics kids. Finishing up the unit here on light. We got to get done with this darn thing. A couple last things. One, rainbow. Two, white clouds. And three, blue sky. Now, the idea that you should have caught earlier in the, in this unit, if you're looking at the notes, is like right here. What can happen is that it says different wavelengths travel at different speeds and actually get bent by traveling through pretty dense media. And a prism is an example. And what's even really more cool is that a water droplet can be an example. So on the left at the top there, you got a water droplet. So the light from the sun hits that water droplet, and you notice in the picture what happens to the colors. They break into Roy G. Biv. And the blues are bent more because they're so small, they're affected more. They're bent more than the reds, and so they're really bent. And then you've got total internal reflection going on right here, and then it bounces back and comes back towards you standing over here. So what ends up happening, it's really kind of cool. You got to have a couple of things necessary in order for there to be a rainbow. One, you got to have sunlight. Two, you've got to have some sort of droplets in the sky. It doesn't even have to be water droplets. It could be like snow. I've seen it around the sun with snow particles in the atmosphere. Oh, I got great videos of it up in Yosemite at Mist Falls. There's a perfect rainbow in the water mist there. So you got to have water droplets and sunlight. Now, what happens is that as the storm is passing you, so it's coming from, in this picture, it's coming from here, and the storm is going that way or into the picture. And as the storm is going away from you, the water is still falling down in the background. And by you, it's nice and sunny. So what happens is this exact idea here is that the sunlight is split by refraction into its primary colors, and then it ricochets around and bounces back. So you've got uncountable, probably trillions of water droplets doing this right here. And why do you say it's in an arc? Well, technically, it's all over the place, but you see it in an arc because though you're standing somewhere right about here to see this arc, right? Saying somewhere in here. What you're seeing, you're in the perfect exact spot that right there, those are the reflected light photons that are coming to your eye. And so if you walk this way or that way, the rainbow is going to do what? It's going to move with you. And that's why I was a really mean dad when my kids were little. I'm going to find the rainbow out in the hayfield. So he'd go out there, and the poor kid, every time he'd move, it would move on him. And it's like, you're right there. No, Nick, move to your left. And every time he moved, it kept moving. So anyway, that's the basic concept. So you got to have a couple of things necessary for rainbows to happen. You got to have water in the background, and you've got to have light behind you. And here, a double rainbow, that's because you might have two sheets of water, one back farther, one up farther, or vice versa. Then we move on to the scattering, okay? Now, well, these photons are certain sizes, right? And Roy G. Biv, they all have different size wavelengths. And so what can happen is just like a pinball in a pinball machine, it goes in and bounces all over the place, right? Well, the photons from the sun, they come straight through, and we know that clouds are pretty large droplets of water, and that when those photons hit those droplets of water, bing, 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 they bounce all over the place, and they stay suspended in that cloud for, who knows, a fraction of who knows how much of a second. Anyway, they're in there for long enough that all that bouncing around light is what color? It's white. It's all the particles doing it because the particles in the cloud are thick enough. Now, if the water is dense enough, what doesn't the light even do? Well, it scatters around on top, but it doesn't get through all the way to the bottom. And the bottom of the cloud is much darker, meaning it's probably going to rain because there's so much moisture. If nothing comes through, get in the house, hide somewhere because it's going to rain. So that's the idea behind white clouds. They bounce around inside there and rickety, rickety, rickety all over the place, and then they come out and you see them. Now, what happens if there's no clouds? Well, then you get this situation where now there's no clouds, and there is a difference in the size of the wavelengths, as we said. And the larger wavelengths, they'll keep on tooling all the way through, and the shorter wavelengths, like the blue right here, because they're shorter wavelengths, the violet, they'll bounce like a pinball machine. They'll up in the sky just for again, a fraction of a second. And because they stay there for a fraction of a second, it makes the atmosphere look blue. Eventually they do make their way down. Otherwise, you'd have no blue light on the surface, or blue colors on the surface. All the rest of them come all the way through, and they get there eventually. But the little ones here are scattered enough. It's a really gorgeous California Yosemite afternoon, whatever. You get these beautiful deep blue skies because it's near violet, because the air is so clear, there's so few particles that it's only ricocheting around the really, really BIV part of the spectrum, the IV part more. And so it's gorgeous violet color. Now, when the sun is setting, I had a really cool demo for this with milk in a fish tank. But as the sun is setting, it's still doing this, right? Okay, over in California, it's bing, 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 all over the place. Colors all getting there. But here, we're in Wisconsin, let's say right here. The blue light gets scattered out, and then all the rest of them, the greens and everything else, and all that's left over are the reds to get here. So guess what the sun looks like when it's setting? We're looking that way, and the sun looks red. And so the sun is setting, so we got red sunsets, okay? Now, you could have a red sun anytime during the day if what is in the atmosphere? Certain particulates. You get a massive forest fire out west, a volcanic explosion. You can get red sky or red sun during the day because of certain particulates in the air, okay? And so it really does make a difference of why you have a, different colored light to the sun. So anyway, blue sky, scattering, pinballing around the blue, the smaller wavelengths. They can hit the particles and ding-a-ding all over the place. And here at night, the red make it all the way through. The blues over in California, and boom, gone, done. Okay? All right, hopefully that makes sense, and we more or less wrap up with the unit, and I think we're going to have a quiz on this stuff. What did I plan? Come on, I've got it on here somewhere. Where is it? It's the other one. No, that's the one. Yes, here. Okay. Blue sky. Oh, technically, we're supposed to have a quiz. We're supposed to have a quiz tomorrow, but let's have it on Monday on light. Really simple. Okay, trust me, it will not be difficult. Today is Thursday, right? Yeah. Oh, no. This is right. This video is for Friday. I forget, it takes forever to download these stupid things. So anyway, this is Friday's video for right here. Monday, we're going to have a quiz on light. Okay, yesterday was stupid video delays. All right. Anyway, let me know if you got any questions. Okay, bye.